All right, so this is Unit 3, Lesson 1, Part 3. And this one's going to be on radioactive decay and population growth. So these are two like common classic examples of when you use E in like the real life. So radioactive decay and population growth. So kind of your initial, like, I guess your formula that you're going to use, and we've kind of talked about it, but A of T equals E to the K times T. So again, A is your initial amount. E is your natural log. E is not going to change. Okay, so again, E, you use your calculator because it's a number. We've got our growth rate, which is K. So again, it's either your growth rate or your decay rate, whatever it is. And then T stands for time. And this is your final amount. So the problem is we've got the element strontium, okay? Strontium, which his half-life is 28 years. So this is a radioactive decay. This is a decay example. So half-life equals 28 years. The quantity of strontium is represented by the function y equals 10, 1/2. So again, that's where the half-life comes in, t over 28. So the question is, what is the initial mass? What is the initial mass? And then how much of the initial mass is present after 80 years? So if I want to try to figure out this problem, and I want, again, my initial mass, I have to think about, what is the half-life, or what is my exponent going to be? What's my exponent going to be if I want the initial amount? Well, the initial amount is going to be when t equals 0. That's what you started with. So if we say that this is 10, 1/2, if I plug in a 0 here, 0 divided by 28, anything divided by 0 is going to be 0. Well, that's 1/2. Excuse me. So, and then if you remember an exponent, so any exponent to the power of 0 equals 1. Okay? So 4 to the power of 0. Anything to the power of 0 equals 1. So this whole 1/2 is really like 10 times 1. So my initial amount is going to be 10 grams. And now the question says, well, what is the initial mass? How much is left after 80 years? So I'm going to take my formula, 10, 1/2, and I'm going to plug in an 80 instead of a 0 this time. So let's try to figure out what is 80 divided by 28. I'm actually going to keep it, we're going to round this to 2.857, so we're going to round it to 3 decimal places. That's kind of your standard. 10, 1/2, 2.857, and then we're going to use this in our calculator. So we actually could just keep it super accurate if we wanted to. Let's say 10. No, that's not right. Clear. 10 times 1/2 to the exponent of 2.857. And you get approximately 1.38. So our answer is how much is left after 80 years? 1.38 approximately, and that would be grams. So that's a decay example. Now we're going to use a population growth example. So the approximate number of fruit flies in an experimental population after t hours is given by the equation Q of t equals 20 E 0.03 t, where t is greater than or equal to 0. So the question is find the initial amount. Okay, we can do that. How large is the fruit flies after 72 hours? And then graph it. How large after 72 hours? So if I want to find the initial amount, I have to plug in a 0 for t. So t is going to equal 0. So qt, e, 0.03 times 0 is going to equal 0. Therefore, I know that e to the 0 is like a 1. And so 20 times 1 is just 20. So I know that the initial amount is 20 fruit flies. How large after 72 hours? Again, I'm going to take my function, 20e, 0.03, multiply it by 72. So I'm just going to plug that all kind of in my calculator at once, and I'll show you why you need to do that. 20, go to my function, e to the, now if I'm going to do the multiplying in one step, I better make sure to use parentheses. Super important that you use parentheses with your exponents or you may not get the correct answer. Close that, okay. 0.03, I was going to say that number's huge. There we go, 0.03 times 72. And that gives me 173.4. Again, you can't have really 0.4 of a fly. So I'm just going to say after 72 hours, it's approximately 173 flies. And again, I could just type this equation. I could type 20e to the 2.16 and then graph that. I would have to make sure that my window goes at least to the 80. E to the 2.16. Oh no, I want to put the function e, so that's 0.03 times my time. There you go.